Welcome to Hidden Layers, where we explore the people and tech behind artificial intelligence. I'm your host, Ron Green. I'm very excited to be joined today by Dr. Risto Miikkulainen, a pioneer in the field of biologically inspired AI, whose work has helped shape how we think about learning, evolution, and the future of intelligent systems. Risto is Vice President of AI Research at Cognizant's Advanced AI Labs and Professor of Computer Science at the University of Texas at Austin. He's published over 500 papers spanning neural networks, evolutionary computation, and cognitive modeling. His work connects science and engineering by exploring how natural systems process information and how these insights can drive adaptive, intelligent technologies. Risto, thank you so much for being here today.
Yeah, it's good to be here.
I'm particularly excited about this conversation because I have been passionate about evolutionary approaches for over 3 decades now, which is kind of crazy to say. You are a pioneer in this field, and this, I feel like it's a little bit of a slept-on technique, like supervised learning and reinforcement learning have taken the spotlight a bunch. But before we jump into that, I want to ask you, how did you first become interested in AI, and how in the world were you were a full professor before you were 30, is that correct?
Mm-hmm. At least a professor. I don't remember the timeline exactly.
Yeah. So how did you get interested in AI? Was it when you were living in Finland? Was it after you moved to America? And then how did you become a professor so young?
Oh, I know exactly how I got interested in it. I saw the movie 2001 Space Odyssey, and there was HAL, and I wanted to do HAL right, and actually have an AI as a companion and help us do better. Yeah. And then from there on, it's been one thing leading to another, and eventually I always wanted to do science and academia, and been very lucky to have these opportunities. Yeah.
Yeah. So you were building neural networks in the late 80s.
Yes.
What was that like?
Well, it was really exciting because it was the second time that neural networks became really popular. The first time was in the 50s with Rosenblatt and 50s with Rosenblatt and others. But then in early 1980s, there was a resurgence of interest, and I actually it was my first year in grad school when I went to the Neural Nets conference in San Diego. There were 2,000 people, and it was really exciting because it was something up and coming and new, and something that seemed like it would change the world, and it did eventually.
Yeah, eventually.
After a while, yes.
Yeah, we're on our third iteration of neural networks, I think.
Absolutely, yeah.
So you started getting involved in evolutionary techniques, okay? And I think about these different techniques. There's supervised learning, there's reinforcement learning, and then there's evolutionary techniques. Can you break down, before we jump in for the listeners, the difference between those techniques and their strengths and weaknesses, just kind of at a high level?
Yes, and there's a good motivation for each one of those, and an opportunity and a niche. So supervised learning is backpropagation, gradient descent. And that's what you do when you have examples of behavior that you want. So you have problem situations and you have the solutions that you want the neural network.
You have the inputs and the known correct outputs.
Exactly. And that might be, for instance, image recognition. Is there a cat in this image, or a car or something? Or it might be answering a question when you know what the answer is. And that's the whole cottage industry, is to come up with such data sets, asking humans to label inputs and give you the right answers. And then we have a really powerful mechanism, gradient descent, that allows you to build a neural network that forms that mapping from inputs to outputs. And a lot of this current AI craze comes from that perspective. It was first deep learning, image recognition, and then an architecture called transformers, where we only predict the next word, but as a side effect, learn knowledge about the world. And it's based on backpropagation, gradient descent, but only in a very limited sense, because you're just predicting the next word in your big string of text.
Right.
So it was a lucky break. We didn't actually know that was going to be possible. But
Absolutely.
But it happened with a huge amount of compute, huge amount of data. That simple gradient descent mechanism actually gave you LLMs. So that's one area. Supervised learning, when you know what you're doing, but also by accident, also when you predict the next word, you might actually, with a very large scale up, get something fantastic. Reinforcement learning originally started from trying to understand animal conditioning, like how animals learn. They perform actions, and sometimes There are good outcomes, sometimes bad outcomes. Hopefully not really bad outcomes, because then you can't learn. But, whether you get sick by eating berries or whether you get stronger, you learn these associations of your actions and their outcomes. And it's based on individual learning by exploring, trying things out, and gradually trying to exploit more, right? Use those good actions that you know are going to lead to good outcomes. So that's reinforcement learning, and it's really biologically motivated. Backpropagation in a sense is also biologically motivated. Evolution is another part of biology. Obviously, evolution in biology has been really successful in coming up very creative answers and designs. Look at all the animals, what they do and how they adapt it to their environment. It's really creative. And that's what we are trying to capture with evolutionary computation. And the big difference compared to, say, reinforcement learning is that we have a population. So it's not just an individual agent that's trying to get better, as in gradient descent or in reinforcement learning. But we have a whole population of hundreds, maybe thousands of these individuals in most experiments. And that means that we can afford to have a couple of bad ones. And that means we can afford to explore solutions that we wouldn't otherwise even try. Let's just see what's over there. Let's see what's over there. What if I do this? That's what evolution allows you to do. And therefore, it allows you to come up with more creative solutions to problems than, say, gradient descent or reinforcement learning. And that's what we try to do.
Right. Within these evolutionary approaches, I kind of think of them almost like a different, learning ontology. And I want your feedback on this. So with reinforcement learning, you kind of have one model and you're trying to learn this policy. And it's almost like I've always thought about it like it's like an individual human, and you have a brain, and you're going through life and you're acquiring knowledge, and you're trying to understand and improve based upon your actions and that feedback. But you can't pass that along biologically. Everything you learn, unfortunately, dies with you. And with evolutionary techniques, it's less about learning within a lifetime, and it's more about giant populations potentially just exploring the solution space, and then through recombination, you are optimizing for that final outcome. Mm-hmm. And so one of the things that I think that people might be thinking right now that are listening to this is how in the world could that work? If you understand neural networks and you understand that you've got a bunch of parameters that need to be optimized, and we're going to use gradient descent, okay, great. Let's go into the details a little bit. Yeah. So if you're using evolutionary computation, how are these creatures, these models, these systems improving over time?
Yeah. Well, there are many different alternative ways of doing it, but the simplest, most logical one, perhaps the most compelling one, is to model biology. So you have large populations, like you said, and initially, in computation, we start by setting them up randomly. Let's just say that we're evolving neural networks. You could evolve computer programs, list programs. You could evolve rule sets, just simple parameter vectors, parameter trees. But let's just say we're evolving neural networks. So you initialize them randomly, and you have a population of networks that each performs something. It does something differently. And you want to have a lot of diversity. That's what really makes evolution work, that you have different kinds of solutions here. You're evaluating each one. How well do they work? So now the most important part here is that once you evaluated them, you throw away the bad ones, you keep the good ones. And then you recombine the good ones so that you might get the good parts of both parents in one of the offsprings. That's what you're looking for. And there's a lot of randomness. How do you initialize randomly? How do you select the parents? Randomness in evaluation. But what you're looking for, that every once in a while you get a good offspring of good parents. And that's an offspring that's better than your parents are. That's what everybody hopes, right?
Yeah.
And there's this movie, Arnold Schwarzenegger is getting all the good genes and Danny DeVito is getting all the bad genes. It turned out not quite so simple, and that's actually absolutely right. You never really know, in the long term, where the good genes are. And we have even experiments on that. Solutions that perform badly initially might have good genes. And evolution is a way of figuring out what other genes need to be combined with them so that they realize their potential. And that's what the search is all about. you are doing the search in a very large space. It's a population-based search. That's one technical way of describing it. And there's a lot of randomness, so you can explore, but you are utilizing the evaluation so that you can focus in on those that are most promising. And that's what gives you the power.
One of the things that I remember vividly about the 90s when I was working on neural networks was there was this sense that it wasn't like real science, right? That it was more of an empirical study, and that we were kind of throwing things against the wall. This was sort of at the end of the second phase of neural networks being popular. And one of the challenges there was everybody. One of the big concerns was, were we just going to find local optimum, like on this giant, fitness landscape? And one of the reasons I thought evolutionary approaches were so fascinating is it might be a way to work around that, right? You could explore the space in a much, much more broadly, not get locked into some approach that might be positive, but positive in some local sense, not in some global sense, right? So people listening to this who are really familiar with, let's say, traditional modern, supervised learning techniques are probably thinking, how in the world could you explore multiple models at the same time, like computationally, that might just be prohibitive. So you've done some stuff on surrogate modeling that I think is just fascinating. Can you kind of talk about the surrogate modeling and how that is a really powerful technique when combined with this population approach?
Yeah. I want to answer first about the search, though, that yes, local minima is one aspect, and actually mostly it's deceptiveness of the landscape. So that you have many bad solutions, but in the middle of those, there might be a really good one. And if you're doing gradient descent, you'll never find it.
That's right.
And that's why population-based search works, because you can spread out your individuals, and they can be in all of those local peaks and even valleys. And when you do crossover, you might find something that's in between that you wouldn't anticipate.
Right.
But that's just one aspect of scaling up that evolution gives you. Another one is really, really huge search spaces. Because you have a population, you have many individuals, you can spread them out and you can cover a lot more space than any of the reinforcement learning or gradient descent techniques. So for instance, some colleagues of mine did a study on multiplexer design, where you're trying to design a circuit for multiplexer, just as a challenge problem. And they found out that you could scale it up until you are doing 70-bit multiplexer design. So 70 bits means that your search space is 2 to the 2 to the 70th. That's how many states you have. And that is kind of hard to understand, but if you print out that number, and it's as a decimal number on a piece of paper in a 10-point font, it takes light 95 years to go from the beginning of the number to the end of the number. That's the number of states. And you can still find solutions because you're doing these crossovers. And, if you have some parents that have some part of the problem solved, the crossover means that offspring has both parts. And this way you can actually find these solutions in a space that is of that magnitude. So that's the second piece. The third one is just how many knobs do you have to turn in order to solve a problem? Humans can handle about 7 ± 2 from psychology. Bayesian optimization, maybe 10, maybe 15. There are new techniques that allow you to scale up a little more. And as an experiment, Colin Moy-Deb did this study where he kept expanding the number of variables in a metal alloy manufacturing, this melting process, multiple stages, up to billion variables. So you have billion knobs that you have to turn at once in order to find good solutions. And you can do it with evolution with these techniques. So it has this property of not just getting around local minima, but massive scale up and massive exploration and promise of finding good solutions. And what really excites me about AI is that it can do more than I can. I can build a system that can be better than I am in a couple of ways. And evolution is on steroids on that. It can find these solutions you never even think of. And I could go on and give you a couple of examples, but that's what makes it so much fun.
Okay, I want to dig into that. Okay, because I remember in the 90s, again, going back, Carl Sims and the life forms that he evolved in that sort of 3D simulation. I think that was one of the life-defining moments for me that just blew my mind. Yeah. And I can think about, this has happened many times. I remember, NASA used evolutionary techniques to design antennas, and they were just radically different than anything a human design. I want to go back in a minute to their surrogate question, but let's stick with this sort of design space, these sort of unexpected designs. Like, what are some of the most surprising, shocking things you've seen come out of these evolutionary techniques?
Yeah. So there's a whole fun paper put together by the whole community about the surprising solutions from evolution computation. I think it appeared in A-Life a couple of years ago, and people just told stories about what they'd seen, and that's really fun reading. I recommend that. A lot of them actually are finding bugs in the setup or exploiting things that you don't think are there, but they're actual, real, true contributions too. So one of the things that we did was cyber agriculture. So you have a container where you control everything that goes in there: the temperature, the light wavelength, light period, light intensity, nutrients. Everything is computer controlled. So how do you actually grow, say, basil as well as you can? Well, if you're a farmer, you know a lot about your patch of land and you know what to do there. But what if you can control everything? Turns out we have no idea. How do plants what do they actually want to see? So we were working with basil because it's relatively quick to grow. And we had about 300 plantings, recipes. Some of them were known, good growth recipes, and others were just exploratory, different kinds. So we could actually learn from, some innovation. And then we ran evolution with surrogate modeling to try out 3 million different kinds of recipes. And what we found was that basil doesn't need to sleep. You can turn on the lights and have them on 24 hours. This was really a big surprise. The biologists, the botanists, they did not expect that. We initially said 18 hours maximum because we thought that the basil would burn out, but turned out it actually thrives. In 24 hours of light, it becomes bigger, it becomes tastier, and now we know something we did not know. A scientific fact that actually is interesting, and we can study a little bit more now. Where this is coming from, and should we actually do that in all kind of vertical farming?
Right.
So that's one example.
Yeah, and that's an example of where you're essentially operating at to me almost like sort of a meta level. And I'm going to come back to this as well, which is this idea of almost like hyperparameter optimization as this meta problem that you're solving when you're using, let's say, supervised learning or something like that. Okay, but I'm going to come to that in a second. Let's talk about surrogate modeling, because if you're building a population, if you have thousands even, but you can obviously have millions, billions of examples within this genetic population. If computationally, that could be very explosive, even with parallelization and things like that. So the surrogate model, let's talk about that and how that can help.
Yes. Well, maybe the most compelling reason for having surrogate models is that it's just too costly and even dangerous to evaluate the candidates in the real world. I mean, that's what evolution is doing. It's giving you a lot of candidates, millions, and you have to tell how good each one of them is. I mean, the same in the reinforcement learning. I mean, we don't know what the optimum is, so we can't do gradient descent. We can try things out, see how well they work, but you have to evaluate them. Now, what if you're designing treatments for patients? Well, you don't want to try a treatment, surgeon or something. What if you're making investment? Well, you lose your money very quickly because you have many bad solutions before you find good ones. So the surrogate model is often just a gradient descent-based model of prediction that gives you, in this situation, what does this action result in? So you're getting from context to an action to outcomes. And it could be, you have all this historical data on patient treatments. You know how well they recovered in certain treatments. Or in this case, the case of the cyber agriculture, these are the recipes that we tried, and this is how well they turned out. And now you've built this predictive model, and there are some techniques to make it also extrapolate beyond what you already seen. And now, instead of deploying something in the real world and having to just see what the cost is, you actually ask the surrogate model. And you can do that millions of times. It doesn't take 3 weeks to grow, to ask it, like basil. There's no danger. And then you can alleviate the cost and also speed up the process and make it more extensive. Mm-hmm. Now, you have to have a good surrogate model, and that's an art of its own. Right. And then, like I said, the extrapolation is an art of its own. Because typically in the real world, people have only deployed solutions they know are going to work, but you need to have solutions that are different. So in Basil case, we just planted a few. In some cases, you can collect data like that. In other cases, like patient treatments, you really cannot. So you have to make some clever inferences to build that surrogate model. You could also have a simulation as a surrogate model. And if you're doing physical design, machine parts, a wing or something like that, there are really good physics simulators, first-order simulators that you could use as a surrogate model.
Right.
Interestingly, they tend to be very expensive too. So when we did COVID-19 prescriptions, like should we close the schools, should we run buses or not, and things like that, government decisions. We wanted to use first principle simulations, the basically epidemiological models, and ask how would the cases progress. But it turned out a good model would take so long that even if it's a surrogate model its own, we have to build a surrogate model of the surrogate model that's actually quick enough that you can ask million questions. And that has become kind of an approach that people build now, really complex simulations, which is possible finally. But they are too expensive, so you build a neural network that simply imitates or emulates that big surrogate. And now you have a fast enough so that you can have an evolutionary search, exploratory search with the surrogate.
Right. And these neural network sort of surrogates are fairly large now compared to what we used to have, and it makes me think of the work that came out of Anthropic recently around the sort of the surrogate models that they're using to understand the semantics or sort of concepts within the model, right?
Yeah, that's an interesting idea too. You could use. Oh yeah, that's actually really great. So that was one example where you build a surrogate model simply because it's more transparent than the original model. And when you have large neural networks, they are very opaque. They're very hard to understand. So if you go, and the Anthropic model was still a neural network, but it was kind of encouraged to form more local representations that you could interpret. But you could go even further. You could build a surrogate model that's a rule set of rules, something legible, something readable. And now, so you first train your neural net, it performs well, then you evolve a rule set to emulate that. Now you have to evolve the rule set because there's no gradients that you can use in such a discrete structure as a set of rules.
Right.
But evolution is perfect for that. I mean, you can modify the rule structure, you can modify the labels in it and elements and so on. And maybe you replicate 99% of it or 95% of it, but you can actually read those rules. And you can even use an LLM to look at the rules and then explain them in plain English and gain insight into the domain or what's actually happening.
Yeah, exactly. Okay, one of the areas I'm really, really excited to chat about, and I think it is, again, something that is a little underappreciated. We see these waves in AI, right, where something becomes popular, everybody moves towards it, and different areas are sort of underexplored. I think this is an area that's being underexplored, namely using these evolutionary techniques as a meta technique for optimizing neural architectures and hyperparameters. You are a pioneer in that field. It's one of the things that I'm most excited to talk to you about. Can you talk us through your initial work in that area and what you found and what you think, researchers that may be hearing this for the first time, how they can leverage that in their own work today with these modern approaches?
Yes, it's neural architecture search and generally meta learning, which means you learn the loss function, you learn the activation function of the net, or even the learning mechanism itself, the equations that govern the learning. That's a very good application for search, for evolutionary search. And for a while, people were coming up with new architectures every week for image recognition or for language processing, speech processing. But then, of course, now transformers are more or less taken over. That variants of transformers are so much more powerful than what we came up with otherwise. But that's still work that needs to be done with transformers. So there are now alternatives to transformers that we could evolve and get more performance out of that, especially when we get out to the real world. So there are a couple of reasons why we want to do it. There's always the need for better performance.
Yes.
Now, if you are predicting whether the patient will recover from that drug or that. Any amount of better performance or money, any amount of improved performance will make a better outcome. So you don't care about scale or anything. You just want better performance. So you optimize those hyperparameters really well, and you optimize the architecture. How many channels? How many layers?
Right.
And also even the connectivity within them. And we haven't really explored a whole lot within transformers of the different architectures. Part of the challenge is that they are so large that if you modify the parameters, evaluation becomes really expensive. It's already like you can only train one GPT. I mean, because it's one-off, and everything is one-off.
Right.
So if you're doing evolutionary or architecture search in general, you have to try different things, and everyone has to be trained. So, and they don't always transfer from small architectures to large architectures. That's a problem we still have to solve.
That's a really good point. Like the emergent behavior complicates things.
Yes. So you might have a really good performance in a small scale, but it somehow doesn't happen in a large scale. In a large scale, something else happens that you can't anticipate. Right. We don't understand that yet, and that's work that needs to be done in order to really utilize architecture search to improve transformers. But there's another reason why it's already really useful, and that is indeed resource limitations. I mean, you might want to have, a large language model on your wristwatch, or refrigerator, or shoes, or something else, all over in IoT kind of fashion. And you have then limitations in hardware, how much you can actually fit. So you have to have a smaller model. You might want to utilize FPGAs so that you can very quickly, build an application, or generally just neuromorphic hardware, which is another area that's coming out, has been around for a long time, and now has an upswing, putting neural networks in hardware. There are all kinds of limitations on size, but also just the connectivity and other things that you can have. And that's where neural architecture search can really play a large role, because you have so many constraints, and humans can't handle them, but evolutionary search can actually find optimal architectures, and that can make a big difference when you have constraints.
Right. Okay, I want to ask you now. This is we're kind of getting into meta territory here about using these evolutionary techniques around understanding deeper concepts like how language evolved and how intelligence evolved and things like that. Can you talk a little bit about how evolutionary computation and design can allow us to answer some of these questions that, historically we've accomplished almost nothing there?
Yeah. It is fascinating that we are now on verge of doing that. So what made AI really work, like I said earlier, huge scale up. We had 1 million times more compute in 2010s than we had in the 1990s when I got started. And we were struggling. We were trying to get neural networks to do, just variable binding, duck driving a car, and you never seen that happen. And it wouldn't work. And it was nothing wrong. It was just that we did not have the scale.
Exactly.
And we didn't know that. But then 1 million times more compute and things started to work. And from the 2010s, 40,000 more compute, and we get LLMs. What happens when you get another 100,000, factor 100,000? Maybe we get something that is very close to the brain-like computation. Right. But and I forget what the question was.
No.
It was yes. Okay. So given that it was scale up that gave us AI, that's one thing that we haven't yet done. In evolutionary computation, we don't really use that huge amount of computation, and we could. And there are some really good reasons why you should try. For instance, evolutionary computation now is geared towards being really ambitious. You want every offspring to be as good as possible. You throw away things immediately because you're so ambitious trying to get and kind of you don't have any patience. You make progress all the time. That's not biology. Biology actually has a lot of patience. There's neutral mutations that don't hurt you. Even if you have bad mutations, you have some other good qualities that compensate. So even bad mutations stay around. And there's deep time, like really deep time. It takes a long time for things to evolve. And we are not utilizing any of those yet in evolutionary computation. And we could run with a really large computational setup, run something that's more like biological evolution that would probably be more creative than anything we have now. And we could build a model of something like intelligence, how intelligence emerges. Another aspect that we need to solve is environment. We have to be able to model an environment where intelligence actually matters. If it's just animals foraging and running away from predators, we already have many simulations like that. Like you mentioned, called Sims. That was already happening 1990s like that. But now we could have much more complex environments. In particular, one ingredient that's really crucial is to be able to leave, to make a change in the environment. Build something that stays behind you. You mentioned we die and we're gone. No, we write books. We compose musical pieces. We leave things behind. Yeah. And then the next generation, 5-year-olds now extract DNA from strawberries in a kindergarten. Yeah. So we are not starting from scratch, and we're leaving things behind. And that is actually probably what allows us to eventually emulate emergence of intelligence. That there's that ability in the environment. Now, there are many theories about intelligence and even language, how it evolved. For instance, that communication is one thing. And there's lots that's now known about animal communication. Dolphins, we can actually describe their language, even though we can't quite talk to them yet. And chimpanzees, bonobos, various ape species, they seem to have ways of communicating with squeaks and various vocalizations. But humans are the only ones that really put elements together into a structure that's productive and systematic. Yeah. That's language. So how did that evolve? Where did that come from? And there are theories. And one of those is the society that requires different roles at different times. So animals at one time they are parents, one time they are hunters, then they groom each other, and they can switch these roles. So once you have a mental structure that individuals can play different roles, you have the structure upon which you can start putting verbs and nouns and subjects, objects, so on. Mm-hmm. That's one good theory. Another theory is that evolved from communication and then the social aspect. Another theory is cognition. We started to have symbolic thinking. Like, for instance, there was a kill. I want to communicate that it's this old and it's in that location, displaced in space and time. And we need symbols to actually address that. And that's another aspect. Even apparently Neanderthals had symbols, they had art, and that kind of is a step towards that. And maybe that's the now we could build a simulation that can test these theories.
Exactly.
Now, it has to be a complex environment. We have to have enough compute. But we could start with some predisposition towards symbolic thinking or predisposition towards communication, and see under what constraints we get language to evolve. And it'll be fascinating to see what happens. Now, a little bit fast forward here. The really great opportunity now for AI is to have multiple AI agents talk to each other. And we can run a complex organization this way, in a way humans never can. Humans get siloed. They have to follow simple rules. And there's never really a good way of... all kinds of errors happens all the time. Organizational equivalent to painting yourself into a corner, for instance. Things like that happen. But with AI agents, they could actually do a much better job. Now, and the reason why we can do it now is because they talk. They have natural language interfaces. We've been working with multi-agent systems for decades, but they never really took off because it was so hard to get them to talk.
That's right.
Now they can. But if we crack this language emergence thing, the AI agents can develop their own language, one that's really much more efficient than a human language. It's efficient in the job that they have to do. And we can avoid, say, logical errors, which humans misunderstand each other all the time. I mean, just a little tiny bit is communicated. When I say something, you filling in all kinds of blanks, maybe 80% of the understanding is actually filling in from your own background knowledge.
Right.
Now, we would develop a language for these multi-agent systems that is more efficient in the communication. You communicate exactly what you need to do. There are no ambiguities, and there's no need to try to guess what's being communicated. And therefore, much less error-prone, much safer, more efficient. Mm-hmm. Fascinating topic for the future. But we have a couple of problems to solve along the way. But that's what I see coming up in the next, 10 years or so.
All right, I want to ask about your new book, Neural Evolution, Harnessing Creativity and AI Model Design. Hold on. I screwed up the title.
Okay.
I want to do that right. I said
Good.
and said. All right, I'm going to ask you about your new book coming out, Neural Evolution, Harnessing Creativity in AI Model Design. It's going to be published by MIT Press. Is that right? Can you talk about that a little bit?
Yes, it should come out in very soon now. So it is a first comprehensive book about this area of using evolutionary computation to optimize neural networks from all the different angles. We touched upon many of them. Most of it is about behavior, creating intelligent agents, but part of it is also about creating neural architectures, architecture search, meta-learning. There's also evolution of language. There are combinations with LLMs, combinations with reinforcement learning that are important. And it gives a comprehensive view of where we come for 30 years and where we likely to go. And I believe that this is really an important aspect of the future. We are going to have probably a period next where we will see many new architectures come out. The transformer-based LLMs is one really great one, but maybe people will have to have smaller architectures serve many more tasks, and they might be different. And I believe that neuroevolution can play a role in that kind of customization. And that's why we wrote the book. I wanted to do it in 2002, but new ideas kept coming out all along, and we never could actually stop. And finally, we decided now is a good time because we really need to see the need for it going forward. And I have co-authors, Sebastian Risi, David Ha, and Jijin Tang. Some of them are in industry, others are academic, because that's also what's changed. That academic and industry work really closely together. Whatever discoveries are made, wherever, it doesn't matter. It's the same community. So we hope that there's also therefore a bridge to making practical applications.
Yeah. All right. Well, I want to wrap up with, this is not so much a question, it's a statement. We had Hinton, LeCun, Bengio win the Turing for essentially supervised learning a few years ago. And then we just had Bartow and Sutton just a few months ago win the Turing for reinforcement learning. I am so excited to have you here because I think there's a legitimate chance that your work is going to get the recognition it should with the Turing Award in evolution, which I consider to be on par with these learning techniques. And I think the world is just sleeping on this still, and they're going to wake up to it soon.
Yeah, that would be great, but we do have some work to do.
Yes,
that happens.
There's always work to do.
Yeah.
But Risto, thank you so much for coming on board. I am just so appreciative you took the time.
Thank you. My pleasure.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.